This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, guys. I think we should make a start. Okay, right, so welcome to Lecture 4. Before we start, just a couple of announcements. So, tutorials, F4 Lab, and MATLAB workshops start next week, okay? So if you go to the tutorials this week and you don't see anybody there, it's because it's not happening yet, right? So everything's going to start next week, okay? And for those of you who have not registered for an F4 Lab, or if all the F4 Labs are full, if you have not already emailed me or contacted Morgan, who is the head tutor of this subject, please do so she can organize a session for you, right? And if you have already emailed her, please just be a bit patient. Hopefully the sessions will be available sometime later this week, okay? Right, and also another thing is I've been getting a lot of emails from students saying that they want to have the lecture slides before the lectures. So yeah, I've uploaded these slides. I've called them pre-lectures because they are lecture slides from a couple of years ago, right? I can't guarantee you that the lecture slides are error-free. Okay, I might have made some changes since then, but I guess it's probably an alright guide for you to have a look before the lectures if you want to. Okay. All right. So last week I introduced to you this smoker's problem, right? Where we have two guys here, Harold and Kumar, right? Who is smoking, and there's a bystander some distance away from them, which I've defined as L. And above the smokers, there's an exhaust, right? And we want to find out how far must this bystander stand so that he or she doesn't get killed by the secondhand smoke. Okay? And we are going to use the simplified inviscid two-dimensional incompressible equations, our Euler's equations, right? And to find out how far this bystander has to stand, we need to know the streamlines pattern in this flow. Right, and again, a recap from previous lecture, we know that the equation of a streamline for a two-dimensional flow is just v dx minus u dy equals to 0. Okay, and we know this because for a streamline, the cross product of ds with v, the velocity vector, is equals to 0. Okay, and that's how we derive this equation here. Next, I introduced to you this function, this stream function called psi. Right, and we have defined this stream function psi so that it automatically satisfies continuity. Right? So u, our velocity u, is just equals to del psi del y. Okay? And our velocity v, which is in the vertical, is just negative del psi del x. Okay, and if you do substitute this definition of a stream function into our continuity equation, right, you do see that it automatically satisfies continuity. Okay, it conserves mass. So what does this stream function represent? What does psi represent? Okay, and we found out that a line of constant psi is basically your streamline. Okay? So if you have a streamline for a flow over an airfoil, the value of psi along that streamline is a constant throughout, right? The next thing we had a look at is what's the physical meaning of psi, right? Does the value of psi have any meaning, right? And we started off by considering two streamlines, okay? Streamline with psi 1 and another streamline with psi 2. And we draw a line between these two streamlines, and we considered the mass flux across this line, right? So we consider some small distance, ds, right? And we did a control volume analysis in this small element here. Okay, and by continuity, we found that VDS plus VDX equals to U dy, all right? And that's just from the conservation of mass, from continuity. Okay, and if I substitute my equations of a stream function into V and U, and rearranging the equation, you can see that these terms here on the right hand side, that's just equals to d psi. Okay, hopefully you can see that. Now, as I integrate my equation between streamline 1 and streamline 2, okay, the integral of d psi is just going to be psi 2 minus psi 1. Okay, and on the left hand side, that's just going to be the volume flow rate between streamlines 1 and 2. Okay, so the difference in the value of psi gives you the volume flow rate. Okay. After that, we then derive a few stream functions for different types of flow, for simple flows. All right. We have this one here, which is a uniform parallel flow. So we know that velocity u is u infinity. Right. So u is equals to del psi del y, and it's equals to u infinity. And the vertical component v is 0, therefore I get del psi del x equals to 0. And if I integrate this, okay, and if I compare the equation on the left hand side here with the equation on the right hand side, I know that psi is just equals to u infinity times y. Okay, so this equation here will give me an equation for a uniform parallel flow. And similarly, I can also derive the stream function for a free stream flow at an angle of attack. Okay, and if you do the maths, which we have done last week, you should be able to see that psi equals to some function of cos alpha and sin alpha, right? Now, the problem is these simple flows, they don't actually help our smoker's problem. Okay? We therefore have to introduce something new today, which is a source and a sink. Okay? Right, so before we go into a source and sink, we derive the source and sink, it might be useful for us to express our stream function in terms of cylindrical coordinates. Okay, so let's start with our Cartesian coordinates, where u equals to del psi del y. Okay, and I can expand this in terms of r and theta, so I can get del psi del theta del y plus del psi del r del theta. Okay, hopefully you should know this. That's basically the product rule, right? Okay, and finding the relationship between x and y with r and theta. Okay, I can then show that del theta del y is equals to cos theta over r, and del r over del y is equals to sin theta. Okay, I'll let you do this as a homework, but you should be able to find this relationship here. Okay, and all I'm going to do is I'm going to substitute that back into my equation u. Okay. Right, so my left hand side now, I'm just going to express that in terms of ur and u theta. Okay, that's what I've done. Okay, and if you look at this equation here, sorry, before that, we can also do something similar for v. Okay, and you should be able to get an expression for v which looks something like this. Okay, now if I compare the cosine terms, right, Okay. And if I compare the sine terms, right, can you all see what my stream function looks like? Del psi del r and del psi del theta. Kinda. Right, you can see it, right? So basically, I'm going to get u theta equals to negative del psi del r, and ur is going to be equal to 1 over r del psi del theta, okay, just by comparing the terms just by comparing the terms in this equation here and also the equation below, right? Just by comparing the cosine and sine terms, okay? There is an alternative derivation, and that's on page 21 of your lecture notes, so please have a look at that as well. Right. So previously we have looked at our uniform parallel flows, okay, but now we want to introduce a source and a sink, which I guess is more relevant to our smoker's problem. So the definition of a source is where we have some radial velocity going out from a point, okay. Right, as you can see here, it's moving radially outwards. That's a source. Okay, and the azimuthal velocity u theta for a source is 0 by definition. Okay. Now, at any radial position, the total volume of flux must be equal to Q. Okay, that's just conservation of mass. Okay, so if I take this control surface here, which I've defined as 2 pi r times 1, so 1 is just a unit depth. My flux, my total volume flux is going to be equal to 2 pi r times 1, the unit depth, times ur, okay? And this has to be a constant, okay? So rearranging it, I can get an expression of ur in terms of q and r. And u theta, as I mentioned before, is just equals to 0. So I know what my radial velocity and my azimuthal velocity is, so I can substitute it into my definition of a stream function in cylindrical coordinates. Okay? Which is this one here, these two things. Right, so substitute for ur and for u theta. Okay, I get an expression that looks like this. And all I have to do now is just integrate this equation here with respect to theta and this equation here with respect to r. Okay? So if you look here, the r terms cancel out, and I end up with theta equals to psi equals to theta, q theta divided by 2 pi plus f1, which is some function of r. And on the right hand side here, this equation is just f2, which is some function of theta. And by comparing the equation on the left and on the right, I know that this has to be equal to this term here, which is a function of theta, and f1 here is just 0. Okay. So I get psi for a source to be equal to q theta divided by 2 pi. Okay. Now I can express my source flow back in Cartesian coordinates as well. And all I have to do is I just substitute theta here with the arctangent of y over x. Okay? And I get psi, my stream function, for a source in terms of Cartesian coordinates. Right, so it is expected that you know how to derive these equations. Is everyone following so far? Yep. Okay. So that's for a source. A sink is not too different, all right? So opposite to a source, is a sink flow. Basically, you have a negative radial velocity. Okay? So you have a flow going into a point. Right, oops. Right, and again, u theta is equal to 0. Right, and if you do the derivation again, you end up with psi equals to negative q theta over 2 pi. Right, so the only difference is that you have a negative here. Okay, and in Cartesian coordinates, you have negative q over 2 pi arctan y over x. Okay, so you have a negative in your stream function for a sink. Okay, so what we can do then is we can model our exhaust as a sink. Okay, very good. And the smokers as a source. Okay. Yep. So this stream function psi, which we have introduced, it's quite useful actually because it automatically satisfies continuity. Right, we've shown that. It is relatively simple to use psi to define flows. Right, we can define a source and a sink for the smoker's problem. Sorry, we can use a source and a sink to model the smoker's problem. Okay, and because we know the streamlines of the flow, we can also know what the velocities u and v are. Okay. Also, it gives us an indication of a volume flow rate, right? Remember the physical value of psi. Okay, it tells us about the volume flow rate. But we have not talked about the momentum equations. Okay, so what about the momentum equations? Does our stream function satisfy our momentum equations? We know it satisfies continuity, but we're not sure about our momentum equations or our Euler equations. Okay, so let's find out. Let's find out together. So it's a bit small. Okay, so we are starting off with the Euler's equation, right, which is the Navier-Stokes equation for a two-dimensional, inviscid, incompressible flow. Now, we want to express this equation in terms of psi. Oops. Okay, and to do that, we need to do a little bit of mathematical gymnastics, right? So the first thing we want to do is we want to remove the del P terms. Okay, basically the terms on the right hand side. We want to remove these terms away. Okay, and to do that, we would want to differentiate our equations 1 and 2. Okay, I want to differentiate my equation 1, which is the momentum equation in the x direction, with respect to y. Okay, and I want to differentiate equation 2 with respect to x. Okay? So why do I want to do that? So I want to do that because if I differentiate this with respect to y, I'm going to get del p del x, sorry, del squared p del x del y, right? And if I differentiate this equation here with respect to x, I'm going to get del squared p del x del y as well. Okay? And then I can take equation 2 minus equation 1, right? And then I can get rid of these terms here, right? Okay, so let's do that. Okay, those of you who knows how to differentiate equation can straight away differentiate the equation. Okay, because I'm very lazy, I'm just gonna cut and paste. Right, so I'm gonna get, this is gonna be equal to that. Right? Everyone agree with me so far? Now, we want to expand these terms, so we've got to use our favorite product rule. Oh yeah, I'm just going to call this equation 3, equation 4. Right, so if I expand this term here, all I'm going to get is del squared u over del y del t plus, okay, and then if I differentiate this term here with respect to y, I'm going to get two terms. The first one is going to be del u over del y, del u del x plus u del squared u over del x del y. Is everyone okay? You all know how I got these terms? Yes? Yep. Okay. So I'm gonna fire on, alright? So I'm gonna write all the other terms. So basically I'm just expanding it. Del v del y, del u del y plus v del squared u over del y squared. Okay, and that's going to be equal to negative 1 over rho del squared p over del y del x. I'm just going to clean this up a little bit. Okay. Okay, and the momentum equation in the y direction, I'm just going to write it down, okay? Okay, and that's my equation 6. Yep.
For the equation 6,
Yep.
not u del square v by a square.
Sorry, which one? U.
Yeah, we use del square u and del for third term.
Third term.
Yeah. Del square u.
So that's U del V. Oh.
Yeah, del square v.
I purposely did that to see whether you're paying attention. So it's good. No, but thanks for letting me know. Yep, so there is a squared there. Del squared. Good. Okay? Yep. So the next step is to get rid of this term here, right? So I'm going to take equation 5 minus equation 6, okay? And the term on the right hand side just cancels off. Right? At the same time, I want to factorize the equation as well. Okay, so I'm going to take out the del t term. Okay, I'm going to take out the del t term. Oops. Sorry. Okay, so I'm going to get del t, del u over del y minus del v over del x. Okay. Now the next term that I'm going to take out is u del over del x. Okay, and if you go back to your equations, I can factorize that and I'll get del u over del y minus del v over del x. Okay. Plus v del over del y. And that's going to give me, in brackets, del u over del y minus del v over del x again. Plus del u del x plus del v del y times with del u del y minus del v del x. Okay, and that's going to be equal to 0. Right? So once you have factorized this equation, there are certain terms which we cancel out, which we can cancel out. Can anybody tell me what equation is this? Continuity, and continuity is equal to 0. Very good. So this goes to 0. Okay. So I can neglect the last term. Very nice. And I can factorize it further, right? Because you can see that I have this del u, del y minus del v, del x term here, right? So I'm going to get del, oops, wrong color, del over del t plus u del over del x plus v del over del y bracket del u over del y minus del v over del x equals to 0. Okay, and can anyone tell me what this is? Total derivative, right? Exactly. So I can rewrite that as the total derivative operator. So it just becomes d over dt del u over del y minus del v over del x equals to 0. Okay, and now I can put in my definition of a stream function. So u equals to del psi over del y, and v equals to negative del psi over del x. Okay, so d over dt is going to be equal to del squared psi over del y squared plus del squared psi over del x squared. Okay, so basically all I've done is I've just taken this here, differentiate it with respect to y, and then substitute it inside here. And this term here, differentiate it with respect to x, and substitute it back inside. Okay, to get this equation here. Okay, and can anybody tell me what, oops, sorry. Have you all seen this operator before? Del squared, del x squared plus del squared, del y squared. It's actually delta squared. Okay? So this is delta squared, and it's the Laplacian operator. Okay. So I can rewrite this term here as d over dt Laplacian of psi equals to 0. Right, and this is your Helmholtz equation. Oops. Okay, are there any questions? Everyone okay? So, in the exam, they might ask you to derive the Helmholtz equation. Okay, and it is expected that you know or you understand the steps, okay? Don't just merely memorize the work, okay? But understand what we are trying to do, all right? The first step that we have done is to differentiate with respect to x and y because we want to get rid of the del p terms, right? Okay, and then after that, we expand each term in the Euler's equation, right? And then we take the equation in the, I think, in the x-axis, right? The momentum equation in the x-axis minus the momentum equation in the y-axis to get rid of the del p terms. And we can then factorize and simplify it to this Helmholtz equation. Okay, so try and do it yourself at home.
It has to be x minus y?
Yeah, well, you can do it the other way, but then you just get a negative. Yeah, it shouldn't, yeah. Either way is fine. Yeah, but we express it in this way because I'll show you in the subsequent slides what it actually means. Why we did it. Yep. Okay, so last week, sorry. All right, so we have this Helmholtz equation here, okay, which is basically your momentum equation, Euler's momentum equation, and as long as we satisfy the Helmholtz equation, okay, it automatically satisfies not only continuity, but also our Euler's momentum equations, right? So we started off last week in lecture 1 with the full Navier-Stokes equation, okay, and then we simplified it to the Euler's equation for a two-dimensional, incompressible, inviscid flow. And today, we simplify it further to the Helmholtz equation, right? When we express it as a stream function. Okay. Now, there's two common solutions to the Helmholtz equation. One of them is where your Laplacian of psi is equals a constant. So you get a Poisson equation. And the other option is, the other solution, sorry, is where the Laplacian of psi is equals to 0. Okay, and that gives you the Laplace equation. And for this subject, we'll be looking only at the Laplace equation, right, where the Laplacian of psi is equals to 0. Okay, so now what does the Laplacian of psi mean? What's the physical meaning of that? Now, if we look at the right-hand side of the equation, okay, you can see that we have velocity gradient del u del y minus velocity gradient del v del x. Okay, so let's consider these velocity gradients. So I have a fluid element here, okay, in a spatially varying flow where there's del v del x. Okay, so you can see del v del x here, where as I move along my x-axis, right, my vertical velocity v is increasing. Okay, and I have this del u del y term here, where my u velocity, okay, my velocity in the x direction increases as y increases. Okay. So if I consider this fluid element here, which has a streamwise or x length of dx and a vertical height of dy, you can see that this velocity gradients is going to cause my fluid element to rotate. Okay, so the velocity at the right hand side of my fluid element is going to be larger. It's going to be v plus del v del x times dx, which is this small length of my fluid element. And on the left hand side here, my velocity in the y direction is smaller, right? It's just v. So this will cause my fluid element to rotate in the anti-clockwise direction, omega 1. Right, everybody agree me? Okay, and this counterclockwise rotation is just defined as my velocity on the right here minus the velocity on the left divided by dx, okay, which is what I've done here. Okay, and we get that omega 1 is just del v del x. Now, if we consider our other velocity gradient, del u del y, okay, you can see that the velocity at the top of my fluid element, okay, is going to be faster than the velocity at the bottom of my fluid element, okay, and it's also going to cause a rotation, which I've called it as omega 2, okay, a rotation of negative omega 2 actually. Right, so what I get is then I'm going to get u, which is this velocity at the bottom here, minus the velocity at the top, divided by dy, and I'll get omega 2 to be equal to negative del u del y. Right?
But why the velocity is bigger up there and it's
Yeah, so this is just our notation. So we just want to keep our notation consistent, right? So remember our right-hand rule. So if this is my x-axis, this is my y-axis, then the z-axis is coming out from the page, right? Therefore, positive rotation is going to be in the anti-clockwise direction. So I've just kept my notation consistent. Yep. So because I've kept my notation consistent, you can see that actually omega 2 is a negative del u del y, right? So the total rotation, okay, gamma is just going to be omega 1 plus omega 2, okay, and gamma is just vorticity, right? So my vorticity is just going to be equal to omega 1 plus omega 2, and therefore I'll get del v over del x minus del u over del y, which is the Laplacian of psi, right? So vorticity, okay, hopefully you can see, is just the negative of the Laplacian of psi. Okay, so the Laplacian of psi gives me negative vorticity. Okay. So from my Helmholtz equation, where the total derivative of the Laplacian of psi equals to 0, implies that my total derivative of vorticity is equals to 0. Okay, so it basically means that the flow has 0 vorticity. Okay, so let's say I have a parallel uniform flow, right? You know my stream function for that flow is just psi equals to u infinity y. Okay, and if I take the Laplacian of psi, okay, you can see that the Laplacian of psi is just equals to 0. Okay, meaning that my flow has 0 vorticity. Okay, and if it has 0 vorticity, it basically satisfies my Helmholtz equation, which means that it satisfies the continuity equation and also my momentum equations. Okay, so you can see that vorticity is constant along streamline, which is 0. Okay, so the flow is irrotational everywhere. Okay. Right, so we have showed that our parallel uniform flow satisfies our Laplace equation. Okay, so the Laplacian of psi is equals to 0. Okay, and we can also show that for a source flow, okay, if I take the Laplacian of psi for a source, okay, always remember the derivative of arctangent, okay? You need to remember that in the tutorials and exams and assignment, okay? You can see that the Laplacian of psi for a source is also equal to 0. Okay? So it again satisfies our equation of motion, continuity and momentum. Right, so the next question that we have to ask is then, are we able to just sum up simple flows, right? So for the smoker's problem, we not only need a sink, but we also need a source. Now when we add a source and a sink together, do we still satisfy our momentum equation and continuity? Okay, and I can rewrite my stream function, right? So let's say stream function n, okay, is equals to stream function 1 plus stream function 2, which could be a source and a sink, okay? And if I take the Laplacian of psi n, okay, if I take the Laplacian both sides, sorry, okay, I can expand the terms on the right hand side, okay, to look something like this. Right, so on the left hand side I have del squared psi n over del x squared plus del squared psi n over del y squared. And that's going to be equal to del squared del x squared psi 1 plus psi 2 plus del squared del y squared psi 1 plus psi 2. Okay. And if I expand these terms further, okay, and next, if I factorize the terms for psi 1 and the terms for psi 2, right, you can see that the Laplacian of psi n is just equals to the Laplacian of psi 1 plus the Laplacian of psi 2. Okay, so basically we can sum up simple flows, right? And that's because of the linearity of the Laplace equation, right? So if, let's say, my source, which we know satisfies the Laplace equation, is equal to 0, and my sink also satisfies the Laplace equation, then a source plus a sink flow, right, will automatically satisfy the Laplace equation, right? Okay, so we can then just add a source and a sink for this problem. Now, all we have to do next is just add a source and a sink at the appropriate location. So if I have my axis here, x and y, okay, you can see that for psi s, which is for a source, and psi e, which is for a sink, can anybody tell me where these source and sink are located at? Yep. So currently, this equation here is located at the origin, okay? But that's not correct, right? We need to have some offset so that we have our source at some location above the ground, right? And a sink some height above our origin as well, okay? So this is a source and a sink at our origin, but we need to have some offset to model our smoker's problem, right? And I will leave it here for today, okay? And I want you to think of how we might be able to adjust our source and sink to model the smoker's problem. Okay? Thanks.
Yeah, sure. How did you? Yep. What do you take from the so the continuity? How did you say this satisfy the continuity? So
continuity says del u over del x plus del v over del y equals to 0, right? Okay. So if I substitute u into here, it will be del 2 psi over del x del y, right?
Yeah.
And then I'm going to get minus del squared psi over del x del y.
Yes.
So this minus this is equals to
Same.
0.
Yeah,
Same.
yeah,
Yep.
yeah.
So that's why you automatically satisfy.
Yeah. Another question for the derivation of the momentum equation.
Yep.
The equation. You say here d and here d plus dv dx dv.
dx. Yep.
What about time?
No, so we are just assuming at space, no time. We just
Is
assuming.
that correct the assumption?
Yeah. So for that, because we're looking at a volume, control a volume analysis at a particular time. Yeah, not the total derivative.
But with velocity, we say u plus du dt d time and x and
Yep.
why we we apply the time derivative here.
So this one you're just looking at a fluid element. We're doing a control volume analysis on a small element. So it's just
Yeah.
looking at a snapshot. But this one we're looking at as a
Different.
whole. Yeah, as a whole picture. So the fluid is moving and everything.
Yes. Thank you so much. Thank you.
Alright, no problem. Okay. Hey, how's things?
The thing is that for that one, before you write it down, there is a function for the here, the sine, source function, and also when you write it down in by substituting the arctangent, we don't consider the function of
Oh, so this one here, right? If you look,
for the source function.
that's 0, right? Because you can see on the right hand side this equation here. There's nothing which has a function of r, right?
Yeah.
So therefore this constant is actually a 0.
So for the solenoidal coordinate, this one should be 0.
Yeah, but if you look at this f2, right, which is a
Yeah.
function of theta,
Yeah.
if you compare with the equation on the left hand side,
Yeah.
you know that this therefore has to be equal to this one here,
Oh.
right? Because your stream function psi is the same, right? It's a,
Yeah.
this is the stream function. This, sorry, the equation on the left and the right has to be the same.
Let me say,
Yeah.
okay.
That's right. Yeah.
Oh yeah. So is it the what we call du is also in terms of y, and dv is in terms of x. How can we? Yeah, this one. So normally, sorry. Normally we choose the velocity u is in terms of Cartesian coordinate of x. Yeah.
Yep. So this one is just looking at the velocity gradients, del v, del x, right?
Yeah, I mean, when you see like we bring up the changes in the velocity u is based on the y locations.
Oh, okay, because that's du dy, right?
Yeah.
Yeah, so if you look at the previous slide, so you see du dy.
Yeah.
So it means that when y increases, your velocity u increases.
So is that just for the continuity equation?
No, because we just want to find out what does, we have these terms, right? Du dy,
So
what's
straight
d
line
dy,
equation.
and what's dv dx.
Okay.
So that's the velocity gradients, right? The spatial velocity gradients.
Laplace straight line equation
Yeah, so the Laplacian of psi,
sine.
okay, is actually equals to, which is this term here, is negative vorticity,
Okay.
right? And that's
that's
and
why-
how we know this is negative vorticity is from the derivation.
Derivation.
Yeah, it's from the explanation.
I got it.
Yeah. Okay.
To the last question, like,
Yep.
for the tutorial and workshop,
Yep.
do we need to the group teammate should be in the same workshop?
Yeah, for the lab, for the F1 lab, it has to be the same session because your report is due 3 weeks, I think, after your lab session.
Lab session.
So it has to be from the same lab.
The same lab.
Yes.
Okay. Yeah. Thank you.
Okay, no problem.
Yep.